Hello, and thanks for joining this SimScale CFD workshop on LED lighting, and more specifically on the thermal management. In 2019, LED lighting accounted for 56% of the global share of lighting revenue. That was equal to almost 68 billion US dollars. So this is an enormous market. Before we get started, I'll just introduce myself as the host and Matt as the presenter. So hi, I'm Steve Lene. I'm one of the application engineering managers here at SimScale. But the star of the show today is Matt. He's going to take us through the actual demonstration. Matt's got a background in mechanical engineering, and he's worked with CFD for many years now. And he's a valued member of our application engineering team, one of our senior application engineers. So, what do we do here at SimScale? Well, we created the world's first cloud-based engineering simulation platform. And what's fantastic about this platform is just through using a web browser, you can conduct fluid dynamics CFD, solid mechanics FEA, and thermodynamics. So how do you get the most out of this workshop? Well, follow along with Matt. He'll be using milestones down the side, and each of these milestones will represent a major step in the simulation setup and post-processing. If you get lost along the way, don't worry, just open the next milestone when Matt says to do so, and you'll have everything set up and ready to go for the next stage. Please do ask questions as you're going through using the questions functionality, and we'll be happy to answer the questions at the end. The fantastic thing about this is by the end, you will have a working simulation setup that you can always come back to. We advise that you use a second screen to follow along more easily. This could be a tablet or a second laptop or a second screen so that you can follow along with Matt's instructions while using SimScale to set up your own simulation. We also recommend that you use an external mouse for manipulating the model. Okay, that's the introduction from me. I'll now hand over to Matt. Thanks.
Thank you, Steve. So as Steve mentioned, the case we'll be looking at today is a LED lighting fixture. You see a quarter model on the right here. It's cooled via natural convection. You see the large heat sink on the top there. There's some plastic pieces down below as well. The main questions we are trying to solve today include, is the design sufficient to keep the LED junction temperature within an operational range? Does the selected heatsink remove the heat from the system to avoid thermal problems? And can we identify any areas of improvement or for improvement? For instance, a better heatsink design, maybe using different materials for the housing here, and so on. Just taking a quick look at our agenda, there's really 6 milestones. I started with milestone 0 because first we actually have to make the model ready for simulation. So that includes a flow volume extraction and some other geometry operations. We define the gravity and assign the geometry. We will then assign materials, define boundary conditions, generate a mesh and define result controls, and then start the simulation. Lastly, we will spend some time in the post-processor taking a look at results. So enough with the slides. Let's jump out. I'm going to jump out of the slides here and tab over to my SimScale project. Now, this is a project. The first step you're going to do in order to follow along is copy this. So over on the side here, there's a copy icon. Go ahead and copy this and then name it whatever you'd like. You can just follow along as I go ahead. I'll just name this MB and say copy project. Great, so now we're inside of SimScale. I'll give this a moment to load, and I'll go ahead and look at the geometries up top here, and I'm going to start with the LED COB light webinar. The first operation we're going to do here is do a flow volume extraction. So one of the first steps you have to do when running a CFD simulation is you need a CAD body which represents your air domain. Now we have a beta release of our CAD mode for SimScale. I'm going to go ahead and select this and enter CAD mode. The first step will be a flow volume extraction. This is going to be an external flow volume, and I already know my minimum and maximum coordinates here. So I'm going to type in 0 for minimum x, 0 for minimum y, and minus 0.2 for minimum z. Next, for the maximums, I will do 0.25 for x. Same thing for y, 0.25. And then for z, it'll be 0.132. And here we have a preview of the size of the bounding box. Lastly, I will use a seed face. I'm just going to click, I guess, this face, and we can go ahead and select apply. And here we can see we have our flow region. There's an extra body in the geometry tree on the right. Next, I'm actually going to delete a body. So I don't need that ceiling panel here, really. It served its purpose, but I'm going to go ahead and delete it. I'll select the body and delete. And if I show the flow volume, now we just have a void where that ceiling piece was before. Lastly, we will imprint. So what this does is basically splits surfaces at the fluid solid interface. This is always the last step you want to do before doing a conjugate heat transfer analysis. So I apply the imprint, and at this point I'm all set. I'm all set up and ready to start setting up my simulation. So let's go to the top right corner and select Finish. Okay. The first milestone will just include defining the geometry and gravity vector. So let's enter milestone 1. You can expand it via the icon on the left, and under geometry, let's select the geometry section. Here, I'm going to select the second simulation domain, so the one that mentions milestones in it. Why I'm doing this is because I've already set up and correctly done all the steps in the geometry work. So I'll select this and go ahead and select Save here. So it doesn't matter if you made mistakes while extracting the flow volume or if you got the dimensions wrong or anything. Just go ahead and use that LED COB light flow volume milestones, and this one's set up correctly. You'll notice 150 contacts were defined. That's done automatically. They were all successful. The next step is we need to define the gravity vector. So we'll select model here, and we can go ahead and set the gravity vector. Now you'll notice a Cartesian coordinate system in the lower right corner. So I want gravity to be down on the screen. So this is going to be minus 9.81 in the Z direction. So we're done with milestone 1. Let's go ahead and move on to milestone 2. So at this point, go ahead and just collapse milestone 1, move on to milestone 2, and we'll keep setting up. Again, it doesn't matter if you forgot any of the previous steps. Milestone 2 is in good shape. So now we're just going to work on material assignments here. The first one is very easy, is to define the fluid, which is air. And then working with solids, what I did, I'll go ahead and hide the flow volume. I actually grouped and made topological entity sets ahead of time. So there's several bodies which are silicon, several which are aluminum, several which are the different plastics. And so I sort of grouped them ahead of time to make things easy. So let's follow this list. So first, I will select the silicon from our material database. And I'm going to just pick from the topological entity set, select that silicon body. I'll select the checkbox to save. And let's do the same thing for aluminum. Here we have 3 volumes. I'm going to do this for the PET. The heat sink is made out of copper, which is a very good conductor. And the outer pieces of this lighting fixture are a PLA plastic. So at this point, we've defined all of our material properties. There's no unassigned bodies, and we're in good shape. So milestone 2 is now done. Next, let's go ahead and move on to milestone 3, where we define our boundary conditions. So looking at milestone 3, boundary conditions are really defining our inlets, outlets, heat loads. It's really just telling the system what is happening. First things first, I am using quarter symmetry here to break the problem, basically solving 4 times faster than a full-size model. I'm going to use the symmetry boundary condition, and I need to select the symmetry planes. So I'll grab the fluid plane, and there's quite a few solids here that need to be selected as well. Okay, so 12 faces, and I'll do the same for the other side. You can see I have selected 24 faces, so I'm all set. Next, I'm going to define an inlet-outlet natural convection boundary condition. So this will be basically on the far walls and on the bottom. And really what this means is it's just ambient temperature here of just under 20 C, and it's 0 pressure gauge. So I'm going to select these 4 faces, and I will also select the bottom face here. So a total of 5 faces assigned with this natural convection inlet outlet. As I mentioned, air can both enter this face and exit it, but any air that comes in is given an ambient temperature of 19.85. Now, lastly, I need to define a heat load. This isn't under the normal boundary condition section. This is actually under advanced concepts here. There's a power source. I'll define an absolute power source. And this will be, if I zoom in here, this will be my silicon body. I'll just name this boundary condition LED, and it's going to be 8.25 watts. Great. At this point, we're done milestone 3, so we can move on to mesh control and result control. So moving down to the mesh here, we are going to mostly use default settings here, except I will end up adding a few refinements. So I'm going to actually, I already generated some meshes, and I know what it takes to put a good mesh on here. The areas which I require refinement involve basically the heat sink. So I'm actually going to add a local element size, and I'm going to call this fin ends. So I needed to add more mesh density across the heatsink fin ends. And I'm going to define a local element size of 6e to the minus 4. Now, I've already made a topological entity set named fin ends. So I'll select this, and it automatically grabs the group I already set up. Next, I'll repeat the process, but this will be called fin sides. And I'm going to define a max element size of 2 millimeters. Again, I did make a topological entity set here, so I'll go ahead and select save. Now, next I need to define the result controls. So these are incredibly helpful to help judge convergence of a simulation. They're not necessary. You can run a simulation without using these, but pretty much every simulation I run has some result controls monitoring the area that I really care about. In this case, the main region which I will monitor is the temperature of where my heat load is, my LED. So I'll just name this LED. It's going to write out the temperature and give me a graph of temperature every iteration. I can monitor this as the simulation runs. And I'm actually going to do the same thing on the heatsink. So sometimes in natural convection conjugate heat transfer applications, one part of a system will converge quicker than another part. So you could have the LED actually reach an operating temperature, however the heatsink is still getting warmer. So it can definitely be helpful to monitor or have a couple points of reference when you're monitoring convergence. Here I'm just going to grab, I don't have to get every single heatsink fin. I'll just grab about 4 of them. Chances are they're all going to have the same temperature. And I'll just name this heatsink fin. At this point, we're done milestone 4. And let's go into milestone 5 and kick off a simulation. So this setup is completely done. We can go down to simulation runs and select the plus icon here. This is estimating to take 44 to 66 minutes. And I'm going to name this simulation run 8.25 watt LED load. And I'll kick off the simulation. Now, one of the great things about SimScale is you can run multiple simulations at once, and your simulations don't queue or anything like that. So maybe I was wondering how much density, how much basically performance I can get out of this system. I can come into power sources, change this. See, I had already changed it earlier. Let's do 12 watts, and I'll hit save. Let's go down. I'll kick off another simulation. This will be 12 watt run 1. And we can check out those results once it finishes. Now, I've already run this simulation. So let's go ahead and take a look at some of the results. So I ran this back at the end of March. We can see it took 100 minutes and used 27 core hours. I'm going to select post-process the results. Okay, so here we are in the post-processor, and we're looking at temperature. So right off the bat, things sort of, it does pass a sanity check. We see the hottest area is the heat sink. We see a thermal plume above it. This tends to make sense. I'm viewing in Kelvin, which is not very helpful. So let's go ahead and switch it to Celsius. And I actually like hiding the flow region here. So we see a maximum temperature of 91 Celsius. That's great to know. That's sort of the high end of the acceptable operating temperature. And if I swing this around, we see pretty much as expected, the heatsink is by far the hottest part. It's actually spread some heat to this plastic base. You can see where the heatsink fin touches the plastic. It does get very warm there. The outer sections are still quite cool. They're not really affected by the heat load. And what's interesting, you actually see this plastic section is sort of green, we'll say, maybe in the 64, 65 range here. But on the back side, it's probably closer to 58 Celsius or so. Lastly, we do see this sort of very small but definitely visible high temperature section right here in splurge. Now, it may be a little hard to understand, okay, what's this temperature versus here? What's that delta or the difference? So I can go ahead and use a inspection point. So here we're at about 89.75 degrees. And just off to the side here, we're right around 87. So roughly 2 degrees Celsius. I can select my body and we see that 91 Celsius on the part which has the heat load. Now, there's a couple other ways to sort of check the solution here. I usually like to put a cutting plane in and sort of understand the cross section. So dropping in a cutting plane, I'm going to turn off the clip model for a moment. And I am interested in temperature more so. And it'd be actually nice to get this cutting plane split between the X and Y axis. So under position and orientation, I will I'll set X equal to 1 and Y I think actually equal to -1. Perfect. Here we can see the temperature through the system here. I'm going to turn back on clipping. This will sort of cut away the geometry, and here I can see the temperature plot. Of course, what's going on here, we can sort of follow the profile of some of the solids. For instance, the back, basically the back section of the light here. Overall, this really passes the sanity check. I see the thermal plume above. These results can be trusted. They certainly seem accurate. Another option for post-processing is dropping in a particle trace. So what this allows you to do is follow the path of the airflow. I'm going to select the bottom here, and I want to put a particle trace below my heatsink. So I'm pretty much aligning it with what would be the origin if you look at the X and Y coordinate system in the lower right corner. Let's add a particle trace filter, and I have to pick the position to drop this in. So I'm going to left click here, and my particle traces are dropped in. Instead of coloring the trace by velocity magnitude, I want to switch it to temperature. And here we see the particle traces coming up through the system. This is as if it's following the path that a single air particle would follow if you followed one particle from the inlet of the system all the way through until it exits. This is the path it would take. One of the really interesting things I noticed while using a particle trace to post-process is if we're looking at temperature here, the air that is hitting the heatsink is already warm, which is not the greatest design. Ideally, you would like to have really cold air hitting the heatsink. But if we select here or see here and look at the legend, my air is already, say, 60 Celsius by the time before it even hits the heatsink fins. Now, this is not good because you want the highest temperature delta. You want your cold air hitting the heatsink. But if I select sort of an inspection point and just select the green here. But yeah, we're at about 57 Celsius. Now, regardless, it's interesting to understand the path of the particle traces. This does make sense to me, yeah, I think the results are certainly good. Perhaps what I can do is try to open up the gap here to allow colder air to flow up through, and then have colder air hitting the heatsink. Now, I do like the visualization of this system here. So I can actually go ahead and take a screenshot at any point by using the take screenshot icon here on the right. So if I select this, it sort of hides the other clutter on the side, and I'll select take screenshot. And this generates a high quality PNG. Now I can actually download this to use in a report or send to a colleague or something like that. And it's also helpful because you can look at this screenshot and reference it later on. It is preserved and stays in the tree here, and you can take a look at that static PNG without opening the whole solution field. So you don't have to wait for the results to open up. You can just quickly look at the PNG. So in general, this is what I had to show you today. Thank you for attending, and if you have any questions, please reach out to me. Thank you.